Hello everyone, I'm Zhang Xusheng from Nanjing University of Post and Telecommunications. I am honored to present here today. My report is about estimating power consumption of containers and virtual machines in data centers. This is the agenda of my presentation. First, we come to background. The motivation of our research can be summarized as follows. In data centers, the power of physical servers can be measured by power distribution units or power meters. But the power of VMs and the power of containers cannot be measured directly. Accurate estimating and forecast of power consumption in data centers is a cornerstone of better visual resources scheduling and efficient power management. Therefore, the power estimating of VMs and containers is meaningful, but few works focus on the power estimation of containers, especially in the scene where the containers are running on VMs. With the above observation, we are motivated to develop a solution to container power estimation in the scene of containers running on VMs. Firstly, streaming from the demand of real-time container scheduling in data centers and the problem of nonlinear relationship between VM features and power in some servers, we adopt a fast-training piecewise regression model based on decision tree. Second, regrading a container as a group of processes running on the VM. The container power can be estimated by the VM model when the features of containers can correspond to the features of VMs one-to-one. Second, I will introduce the method of our model. This is the framework of our model. To simplify the process, the feature illustrated here is only CPU usage. In order to better understand our model, let's come to stage 2 first. At first glance, it's a traditional regression tree structure, but each leaf node stores the weight vector and the bias of a linear regression model. The value of weights and bias is non-negative. The reason we adopt decision tree is that with the appearance of power-saving technologies, such as Intel Speed Step, the relationship between server power and features become nonlinear, which degrades the common linear model's performance. Let's move back to stage 1. There are several VMs running on the physical servers and several containers running on the VMs. At a certain point in time, we can collect the feature vector of VMs and containers. To cope with the dynamic scheduling of VMs on the physical servers, we propose a universe model suitable for different VM types. We sum the feature vector of the same type of VMs, for example, VM median in the figure, and concatenate the feature vectors of all VM types. With the feature vector obtained, we can find the corresponding leaf node in the light of split condition and the recorded leaf node's model parameters in stage 2. After that, models corresponding to each VM type can be accessed. A part of container's power can be estimated by dot product of the weight vector of the VM types which the container locates in with the container feature vector. And at the same time, we break the bias term down into the bias of each container by calculating the ratio of each container's CPU usage to the sum of all containers' CPU usage. Then, we sum the two values up as the container power. The third part of the presentation is our experiments. To simulate the environment of data centers, we built an experimental environment of OpenStack. There is an OpenStack controller node, an OpenStack compute node, and a monitor node. The monitor node collects the PDU data of the compute node through a serial line at a frequency of 1 Hz. We deployed a collector called collectD on the compute node, which is used to collect the features of the compute node, as well as to read these metrics of VMs through the hypervisor layer. The containers data are mainly obtained by executing the command docker states of Docker. The sampling frequency of collectD and Docker states are also set to 1 Hz. The benchmark we used in our experiments is PARSEC. We deployed 2 VM with 2 cores, 2G memory, and 50G hard disk on the compute node to run the benchmarks. For each VM, the workloads in PARSEC will run 50 times in a Docker container with a single thread and dual threads, respectively. Besides, we also run a Docker container for the PARSEC with dual threads on each VMs at the same time to cover the situation where most of the resources were used, which represents 4 core load on the physical machine. This table presents the experimental setup. The training set is randomly sampled from the runtime data, accounting for 70% of the whole data set. We assign the minimum subset size of our model to 1% of the training set size. For the small training set, we stipulate that the minimum subset size should not be less than 30. We assign the minimum error decrease rate to 20. The evaluation metric we use in the experiments is normalized root mean square error, NIMSE. The equation of NIMSE is listed below. In the experiments, we compare our model with these baselines. We first choose least squared linear model as a comparison, which is the most common power estimation model. Secondly, based on observation, we segment the linear model with the case of single core followed, dual core followed as the split points, dividing the origin linear model into the 3-segment linear model. We choose the regression tree model in CART as the third comparison model. Although regression tree is selected as a comparison model, it does not have the capacity of VM power estimation because its leaf node stores only a value, and the value cannot be directly used as the power estimation of a single VM, not to mention the power estimation of containers. The results of VM power estimation are tabled here. On the test set of all workloads, our model's estimation error is smaller than the other 3 models, indicating that our model performs better than other models on most workloads, while the piecewise linear model has an improvement on the linear model. The improvement is not obvious, and it even drops a little on some workloads, such as Freelance. It reveals that the split points set manually based on co-followed states are not accurate, and the piecewise linear model may not fit the optimal power cave. As we can see from the table, all models are not ideal under the workload of Canyon and DLAP. We analyzed the bulk point of all workloads' power. We observed that the power ranges of Canyon and DLAP are smaller than other workloads with the same number of processes. It is partly due to the type of workloads. From the table, we can find the workloads with excellent performance are mostly simple CPU-intensive workloads, and the dependence between components are similar on these workloads, so they all have good performance. However, the dependence between different components of memory-intensive and I/O-intensive workloads are quite different from those of CPU-intensive workloads, resulting in large error of power estimation. With the VM power model established, we can estimate the container level power. The line at the top of the figure is the power curve of the physical server, and the button arrow represents the server idle power, which is about 16 watts on the experimental machine. The middle two arrows correspond to the power values of the Docker container in VM1 and the Docker container on VM2, respectively estimated by the VM model. To simplify the representation, we color the different workloads Dockers in the same VM with the same color. Although the two caves on the top of Figure 2 are not entirely fixed, the overall trends are the same. The main reason for the gap between Docker power and the physical machine power is when Docker are running. One part of the VM power generated by the VMs in the process of scheduling Dockers is not reflected by the Dockers feature. This part of power is not counted as the power generated by the containers in our model. Moreover, the gap is partly due to the power generated by the physical machine itself, such as the OpenStack's compute node survival detection, which is not included in the idle power. Our solution to realize fast training is rounding the normalized value of sleep points to a specific floating point position. For example, 10.2345's floating point position is 4. From the figure, choosing 4 as the internal floating point training position is reliable with relative high acceleration and acceptable speed. However, during the actual estimation, if the error exceeds a certain series due to the appearance of other task patterns not in the training set, 2 can be set as floating point position to retrain the model. What's more, parallel computing can also be adopted for a shorter training time. Finally, let me conclude my talks. First, our model estimates container power by VM power model to avoid twice modeling error. Second, fast retraining can quickly reduce the power estimation error on tasks with unseen pattern by replacing the old model. Third, our model estimates the power of containers as expected. In addition, we will also extend our work in the future. The major problem of our model is that the linear model does not reveal the dependence between features on different types of workloads. As a result, it cannot achieve outstanding performance on all workloads with a single training. Therefore, in future work, we will study the dependence between these features to propose a more generalized power estimation model. That's all. Thank you for listening.